Combinatorial optimization problems in which we want to either maximize or minimize an objective function are ubiquitous. They show up in electronic design automation, traffic congestion prediction, wireless communication, networking, video stabilization, data centers, big data recommendation systems, and UAV resource allocation. The max cut problem is a classic combinatorial optimization problem in which we want to divide the nodes into two disjoint sets such that we cut the maximum number of edges between them. So in this case, the red nodes belong to one set and the blue nodes belong to the other set. And by dividing the nodes in this way, we cut all of the edges shown in red. And instead of using colors, we can use +1 for spin up and -1 for spin down to denote the two sets. A lot of these problems are classified as NP-hard, which means that as the problem size increases, the resources required to solve them might also increase exponentially. But Ising machines are solvers based on physical systems that naturally tend towards their lowest energy state. For example, magnets placed close together naturally orient themselves to minimize the total energy of the physical system. And this equation, known as the Ising-Hamiltonian, describes the energy of such a physical system. So by mapping these combinatorial optimization problems onto this Ising-Hamiltonian, we might be able to efficiently approximate solutions to these problems using Ising machines. The coherent Ising machine is a promising Ising machine that, instead of magnets, uses a network of optical pulses. Each of these optical pulses represents a spin. The system is provided with an external pump, and above a certain threshold energy, these pulses settle into stable coherent states with the binary phase, so either in phase or out of phase, representing either spin up or spin down, ideally. But because of the analog nature of the machine, the pulse amplitudes take on continuous values rather than strictly discrete spins. So for example, instead of exactly -1 or +1, we might observe +0.85 and -0.91. And this is known as amplitude inhomogeneity. So if this is the energy landscape and we want to find the global minimum, because of amplitude inhomogeneity, the system might get stuck in a local minimum instead. To overcome this problem, many modifications to the standard CIM have been explored in prior work, and it has been shown that all of these perform better than the standard CIM. However, these methods have only been compared against the standard CIM, and no prior work has examined how they perform relative to each other to determine the best performing algorithm. So this study presents the first side-by-side evaluation of 6 promising CIM architectures by developing a unified simulation model. We start by developing unified stochastic differential equations for all of the CIMs. Then we pick a variety of max-cut instances from the BigMac and GSET datasets and evaluate all CIMs on the same problems. We then optimize all hyperparameters for each architecture problem pair through Bayesian optimization, ensuring that each CIM is evaluated under its best performing configuration. We conduct a comprehensive evaluation by assessing all CIMs across multiple metrics. For instance, on this metric, which is success probability for 90% of the ground state energy for BigMac graphs, we find that the CIM with spiking neural network, or SNN, has the highest success probability, followed by the rest. Similarly, when looking at time to solution at the same ground state energy and for the same max-cut problems from BigMac, CIM SNN is the fastest and hence the best performing. While CIMs hold significant theoretical promise, targeted research on the most promising architectures is essential for their practical adoption amid the rapidly growing demand for efficient computation. This study contributes in 2 key ways. First, by identifying promising CIM architectures to guide targeted research, and second, by introducing a unified simulation framework for evaluating future modifications against existing ones.